Hi and welcome to this video about virtual address translation. Now we know that when accessing memory in Windows, and in fact in all modern operating systems, we use virtual addresses, which means that the CPU needs to translate them somehow to where they are really in physical memory, if at all. They could be paged out, or they could be just invalid addresses. We've looked in a previous video at this diagram that shows the address space layout of processes on 64-bit Windows. And so we have some user mode addresses here, 128 terabytes of addresses potentially in user mode for 64-bit processes. And of course we have kernel space having its own 128 terabyte potential system address space. So all these addresses we're talking about here are all virtual addresses. When we call functions like malloc, we get back a pointer. That pointer is a virtual address that is somehow translated to physical addresses or the physical address when making an access. And so in this video, we want to see exactly how that works in terms of the CPU and the support provided by the operating system. So here's what that looks like. We start with a virtual address. And remember that everything is managed in chunks of pages, which are by default 4 kilobytes in size, which means that the least 12 bits of any address is copied to the final address as is. It doesn't go into any kind of translation. The translation is only for the virtual page number, the one that's in the upper set of bits. So the first 12 bits, the lower 12 bits always are copied as is to the final address. So if you look at the final result, what we want to get into is a physical page number where the page starts in physical memory and the offset is just going to be copied from the original address. And of course, the translation is happening by the processor. Why? Because the processor is put into this paging mode. So every address it encounters while executing code, it considers as a virtual address. Even in kernel mode, all addresses are virtual addresses. There's no way to directly access a physical address. If you want to access a physical address, you have to create some kind of mapping from a virtual address to that physical address of interest. This, of course, can only be done in kernel mode. Anyway, the CPU needs to perform this translation, and for that it needs some help. And this help is in the form of a bunch of tables, collectively known as page tables, that provide the infrastructure that the operating system sets up so that the CPU will go through the particular tables and find out where the page is in memory, in physical memory, if at all. There's another thing that is used by the processor, which is very important from a performance perspective, but not important from a conceptual perspective, known as a translation look-aside buffer, or TLB. This is just a cache of recently translated pages, so that if you access memory which is in the same page that was translated recently, there's no need to go through the entire mechanism, and already there's the mapping that knows where the physical page starts in memory. As we'll see, the translation process itself is non-trivial, so this cache in practice is very important. So this is what the CPU is supposed to be doing and getting to a physical page number. However, if the tables indicate that the page is not really valid, then the CPU says, hey, I can't go any further. I'm going to raise an exception called the page fault and let someone else deal with the problem, because as far as I can tell, based on the page tables that I have, that I'm accessing, the page is not valid. So it is not in physical memory. In this case, the CPU is not going to continue execution and let someone else deal with the problem. Usually that would be the memory manager within the kernel. And so, for example, it might be a page that happens to be paged out in a page file. In this case, the memory manager will bring the page back into physical memory, fix the page tables, and tell the processor, please try again. Maybe the address is completely junk, such as address 0, which is never valid in any process. So in this case, the memory manager will turn the page fault into an access violation and set that to the process to be handled in some way. If the process doesn't handle it, then the process crashes. So that's the basic idea. So here's what that looks like in practice. How does that really work? And so when we look at an address that needs to be translated in today's 64-bit Windows systems, we have 48 bits that we need to look at. The highest 16 bits are not really being used simply because the translation is not supported. Well, technically today's processors support even 57 bits for address translation, but Windows doesn't use that extra capability, which is beyond what I'm going to discuss in this video. So we have 48 bits we need to look at. The other 16 bits always have either all zeros or all ones, depending whether the address is a user mode or kernel mode address, and they're not part of the translation process, simply because the 64-bit address space is so vast that processors don't support all of it today, and we don't really need it because it is so vast. So the way this works, that we have this 48-bit address, the lowest 12 bits don't really participate in this translation. They're just going to be added as an offset once everything else is in place. And we have this one data structure called page map level 4, which is known to the processor, stored in the CR3 register on x64 processors, and also stored in the K process structure of the appropriate process. So whenever we have a context switch between threads, and maybe these threads belong to different processes, this CR3 has to be loaded from the value of the K process that is stored in the K process, so that it knows where to start translation for this particular process. And then the most significant 9 bits are used as an index into this page map level 4 table, or PML4 table, selecting a particular entry called the PML4 entry. And this entry is a 64-bit value that has a bunch of flags, and more importantly has the physical address of the next data structure in line. So again, I'm assuming here that the virtual address can be translated to a physical address because it is somewhere in physical memory. So now it points to a particular page directory pointer table, and there could be any number of those, so actually no more than 512. That's why we have 9 bits. So you might be wondering why 9 bits and not anything else. That's probably a story for a different video, but in a nutshell, each one of these tables cannot be more than a 4 kilobyte in size, cannot be different than a page size. So 9 bits, we have 512 possible combinations times 8 bytes. Each one of these entries is 8 bytes in size. We get exactly 4 kilobytes. So now we are pointing to this page directory pointer. And now the next 9 bits in line will select a particular entry from that table, which is called page directory pointer entry. And this is going to point to another data structure along the same lines called the page directory. And again, could be 512 page directories for this particular page directory pointer. And again, we continue with this story. We select another entry within that page directory based on the next 9 bits in line, which is going to point to a page table, which is the last piece of the puzzle here in terms of translation. So now the only thing left to do is to use the other remaining 9 bits here to select a particular page table entry, which will finally point to the beginning of a page in physical memory. In order to get to the particular byte we are looking for, because really a byte is the smallest addressable unit, we need to add the offset coming from the 12 bits, the lowest 12 bits of the address, which never participate in the translation itself. And then we can access, or the CPU can access, that particular byte based on that virtual address. So this is in a nutshell the way these things work. Now, one thing that is supported in today's processors are larger pages, or large pages that have a size of 2 megabytes. So in the case of 2 megabytes, the PDE points directly to physical page that starts on a 2 megabyte boundary, and the least 21 bits are used here as an offset to where the byte is. And large pages have the advantage that they provide a better utilization of the translation look-aside buffer, because a single entry can map 2 megabytes of memory rather than just 4 kilobytes of memory. There's of course a downside to large pages, which is not part of what I can cover in this video. So that's the basic idea. So how does this look in practice in terms of these entries? These various entries look practically the same, almost the same. For example, for a 4 kilobyte page, the page table entry looks something like this. The present bit, bit 0, also called the valid bit, is the most important one for the processor to look at. So the processor looks at this bit. If it's 1, it knows to continue the translation to the next level. If it's 0, it says, well, that's a page fault on my, as far as I can tell. It's going to raise an exception of page fault and not going to continue further. And then the part that points to the physical address is here. For a 2 megabyte page, we don't have a PTE, we don't have a page table, we only have a page directory and page directory entry. So the same idea here, just there is a large page bit here and the physical page address is provided here. And of course we have to add 21 bits, just like here we have to have an additional 12 bits. So they're always assumed to be 0. So that's the basic idea in a very quick explanation. Let's see this stuff in a kernel debugger to make it slightly more concrete and see if we can do these things even ourselves, completely just doing the same work that the CPU does. So if I go ahead and find some process that I want to work with, and so what my point here is that I want to have some address to translate that I know is definitely in physical memory. And since process objects are always mapped and they're allocated from non-page memory, it means they're always in physical memory, so I know I'm not going to get a page fault. Of course, we can work with a different address that does produce a page fault, but I'll leave that to you as an exercise for later. So I'm just grabbing some random process object just that I know it is in physical memory for sure. So in this case, I'm going to treat this process object just like data, because I really don't care about the fact this is a process object. I only care about the fact that it is mapped into physical memory. So looking at the address from a virtual address perspective, which is the only way to actually work with memory directly, we can see it has some data here. So this is the eProcess data structure, or the beginning of that structure. And what I want to do is to perform a translation of this virtual address to physical address, and then see that looking from a physical address perspective of the same virtual address, the corresponding virtual address, we should see exactly the same data. So how are we going to do that? There are two commands the kernel debugger provides us. One of them is called PTE. So if I try PTE, sometimes you'll get this weird error, which is just a bug in the PTE implementation. Sometimes when the symbols get updated with the new version of Windows, an updated version, this command starts to work. However, fortunately, there's another command we can use, which is called V2P, for virtual to physical, that says, give me a virtual address, give me some process context to work with, and then I'll give you the corresponding physical address if indeed it is mapped. And so I need to provide here something called the PFN of the PDE and the virtual address. So what it really wants here is the value that we've seen that is stored at the root of the hierarchy of translation, which is stored in the K process structure and stored in the CR3 register when the processor actually is working for translating for that particular process. And so since we're talking about the kernel address here, this is just an example. We could have used the user mode address just as well, but that would make things slightly more complex to find a suitable address. And again, I'll leave you to do that yourself. Then we need to use the kernel process, because it's the one that's going to store the value of the directory base where the translation actually starts. So if I look at a particular process, in this case I do want to look at the system process, this dir base parameter that you find in every process really, this dir base is the address in physical memory where PML4 starts, where the PML4 data structure resides. It has to be physical memory, it can't be a virtual address, because if this would be a virtual address, how would you translate that? We have to start somewhere, so it is a physical address. So now we have this address here. This is supposed to give us the process context. If I would have liked to translate a virtual address for some other process, say some user mode process like Notepad, I would use dir base for Notepad when giving it an address to translate. So for this V2P, we need to provide this address first, the directory base. And then we need to provide the address we would like to translate, which is of course this virtual address here. And if we do that, we can see that translation works. We can see here the actual values being shown as the translation mechanism is being employed here by the debugger, and the translation eventually says that physically this is in this address. That's the address physically that corresponds to this address virtually. So is that right? How can we prove that? Well, at least we can get some corroboration by taking this address and looking at the same memory that we've seen here from the address of a physical, from perspective of a physical address rather than a virtual address. And you can do that using the db command with a bang here. So these bang d something commands are similar to the normal d something commands, but they expect the numbers here to be physical addresses rather than virtual addresses. So if I go ahead and do that, we can see here a bunch of information, and if we compare that what we see here, it is exactly the same thing. That will be the first line, that will be the second line. You notice the debugger is able to notice that these are the same kind of values. Going to the third line here and so on, it is the same thing. So it is true that this physical address is in fact the same as this virtual address. Now, can we do the same procedure ourselves manually? Let's see if we can make that work. So I'm going to grab this address here, and I'm going to use the formats command to give me a binary breakdown of this address. So we can get this address here. So as I mentioned, the first 16 bits here, the highest 16 bits, don't really count because they are always going to be 1 for kernel addresses and always going to be 0 for user mode addresses. We only care about these 48 bits. So I'm going to grab these 48 bits. I'm going to use Notepad here to help me out. So let's have this text here, and I want to bundle that into the same kind of bucket as we've seen in the slides for translation. So we need to have buckets of 9, 9, 9, all 9s, and the rest is going to be 12 bytes, 12 bits. So we have 8 here. Let's grab one more. So we have now 9 bits there, and then we have 9 bits here. Here we have 6. We need 3 more. So here goes, and we need the 9 here as well. So that's going to be 9, and we're left with 12 bits here, which are going to be the offset. So the offset is never going to be actually translated. Okay, so let's now go ahead and get these numbers in hexadecimal to make it easier for us to work with the debugger. So let's start with this value here. What is that in hexadecimal? You can use the question mark and the 0y prefix, which is for binary. So you can see it's 126. Okay, good. Let's write here. That's 126 hex. The next one is this value here. Let's go ahead and translate that as well. And this is going to be 29. Fine. Let's write 29 hex. We're going to use hex because the debugger liked hex better, even though we could have used decimal here. The next one is all ones, so not very difficult to translate. It's going to be 1FF. That's 9 ones. And then we have this binary thingy. So let's go ahead and translate that as well, convert that. That's 84 hex. So we have 84, and the last one is 80 hex, which is the offset, which would not be part of the translation, but you can already see that as the result that we got here in the translation, we have 080 at the end, which really corresponds to this 080 here. At the very least, it seems like 80 here is at the end, which is what we expect because the least 12 bits never get translated. Okay, so we have that. So how do we continue from here? We have the base address, that is where the PML4 address starts, which is here, the physical address. And we need to grab now the index 126 inside this, into this table, and show the 64-bit value that is there. So we're going to use the dq command, bang dq, because I'm working with physical addresses. I'm going to take the base address, take 129, which is, sorry, 26, which is the first 9-bit value, and multiply by 8 because every one of these entries is 8 bytes in size. That's 64-bit. And I want to have just the one. I want to see that single entry, see what that value is. And you can see this value right here. And if you want, you can go back to this information here, and this value should be corresponding to something like this. So you can see it's a 6D5930 or something. This should be essentially the same. So you can see that this is the actual entry and this is the value there. So the value is supposed to be the physical address where the next chunk starts. But we have 12 bits here which contain various flags, and the bit 0, which is the present bit, is indeed lit up. Notice the number is odd, which means that the 1 bit is definitely lit up, and this would be the address to move forward with the 3 zeros. So we need to now take this address with 3 zeros, because it's always starting on a page boundary, and add the next item in line. The next item in line is 29, so that's the next entry. So let's grab 29 times 8 and then look at what we have there. And we have this value. And with that, we're going to do exactly the same thing. The least significant 3 hex digits here are just these 12 bits, which contain flags, which we don't care about. We care about the offset, which is here. The other stuff, by the way, at the end here doesn't really apply to, it's also include some flags and some other information which is not relevant. So I'm going to get this value here, continue with DQ, this value with 3 zeros because it's always on a page a boundary, and then add the next number in line. The next number is 1FF that we need to use. So 1FF times 8, and again look at the single value that is there. And we have this particular value here. This is what we get inside this value. So what should we do next? So one thing we should note here is that the value that we get here is in fact, might even contain, if we go back here, we can see that in fact we have a large page here. And the value that we see here should be something similar to what we have found here, and we can see exactly that. So there's a large page here. It's bit 7 actually is lit up, which is something we can verify fairly easy by looking at the set of flags here. So this is a large page, which means we have to take this number here and add, well, since it's a large page, we need to add 21 bits to what we find here. And notice that the final address here does start with 116, so it's not really a coincidence there. So we have this 116 here starting with the address, and then have the appropriate addition. So let me use DB here. So because we're at the end of the translation itself, we just need to add the offset. And the offset in this case is these 21 bits. So it's not really 80 and 84. We actually have to take 21 bits. We're going to take all of these 21 bits together, and let's see what that entails. So here's what we get. We get 84080, which means that the final address is supposed to be 116, and then as we've seen here, the address is 1160 and then 84. So that offset. So we have this number of bits we need to actually look at, and we need to add the offset here. So we have that, and that's exactly what we got to begin with. So this is exactly the procedure that the CPU goes through in order to make the translation work. We just need to make sure that we don't mess up here in terms of bits and all that. And you can see that you can do these things yourself with any kind of address that you fancy. Could be a kernel address, could be a user mode address. In the case of a user mode address, you need to select a particular process, which means that for the v2p command, you would use the appropriate directory base for that process, and the address should be a user mode address compared to that process. With the kernel address, you're going to use the system process, as I've done here. This is just an easier way to make sure I can find some memory which is in physical memory. So there you have it. It was perhaps a bit fast, but showing you how virtual address translation works in practice on x64 processors. This is the way it works on Windows, on Linux, and other maybe Mac OS that uses Intel processors. It's exactly the same way that this works, because this mechanism is part of the processor's way of working. It's not up to the operating system. The purpose of the operating system here is to prepare all these page tables appropriately and handle page faults as needed but other than that, the processor is going to use this mechanism to translate any address that it gets. So you better have these page tables and all the other tables laid up correctly in memory to accommodate the translation you'd like to have. The processor will simply blindly move and try to make the translation. Of course, if it encounters a present or a valid bit which is 0, it's going to halt its processing. So if I tell, for example, the v2p command with some random address, so let's just go ahead and use the system process directory base, but use some random address that has no particular meaning, which is unlikely to be mapped to anything. So you can see the translation fails. It says the page directory is here and it doesn't really work because we have an error here. And this is likely because the actual value is 0, which means at the least significant bit, which means the present bit is 0. So there's nothing there. There's nothing there and there's no where to continue here. It says that's a 0 PDPE, which means that even though these things might exist, this one doesn't exist. It has a 0 there at the end, which means it's not a valid page and the CPU cannot move forward, and we get an error here. And that's what happens when you have a page fault on your hands. In this case, the page fault is going to be translated to an access violation if I'd actually try to use this address in practice on this particular system. So this is it. I hope you enjoyed the video. See you next time.